In the last lecture, I briefly outlined what the mechanism was for the SN2 reaction. In this lecture, we're going to use that information to predict some interesting aspects of the SN2 reaction, just look at more examples and try to get more comfortable, predicting products in the Grignard reaction. And so let's start with maybe one of the more simple SN2 reactions, where we take sodium hydroxide plus bromomethane. And I'm going to write the bromomethane as, I guess I would prefer it if we had H3CBr, but it's the same molecule either way. We have delta plus, delta minus, and then what's happening here in this reaction is the sodium hydroxide, when it's added to a solvent, which I guess I could write over an arrow, the sodium hydroxide is going to dissociate in the presence of an appropriate solvent like DMF, for example, which I could include the structure of. It's going to dissociate to give rise to this negatively charged species on oxygen. That's going to be attracted to the delta plus on the carbon atom. Carbon atom can only hold 4 things, and so as to avoid exceeding its octet, we're going to shove off the good leaving group, which is the bromine atom. Now that's going to give rise to, as a product, I guess it's the same reaction in either case. The product that we care about the most is going to be the methanol product, but if you wanted the Na plus to kind of come back in and bind to the Br minus, that would also form a salt byproduct. Okay, so that's me basically putting 2 reactants on a piece of paper and predicting what the outcome would be in an SN2 reaction with an appropriate solvent. We want to be able to do this. We want to be able to recognize that when 2 reactants are together, what the products would be. Now, what I want you to notice is as I solve that reaction, I use curly arrows. Knowing a mechanism and being able to solve the products are 2 skills that go hand in hand. We want to be able to do both of those things at the same time. And so really getting comfortable with the mechanism is important for predicting the products. Sometimes the mechanism is a little bit unwieldy, and so we try to develop a different heuristic for figuring out what the products would be. As in the case of free radical halogenation, right? The mechanism is we have initiation, then 2 steps of propagation to get to the product. And so it's a little bit time consuming to do that for each individual product. And maybe you just say, okay, let's replace a hydrogen with the halogen in that case and make sure we don't have duplicated structures. With the SN2 reaction, the mechanism is simple enough that it's worth, and there's usually only 1 dominant product that we need to form. So it's kind of worth going through, making sure we understand which atom is the nucleophilic atom that's doing the attacking, which atom is the electrophilic carbon that's receiving the nucleophile and pushing off the haloalkane. Okay, what I want to do is take this first example and provide some mechanism with geometry, I guess. So what I mean by that is I'm going to draw the CH3Br with the carbon drawn as a tetrahedral center. So the OH has no molecular geometry because it's only got 2 atoms, but the CH3Br has molecular geometry. To be sure, it's a tetrahedral center where we have 2 straight lines, a wedge, and a dash. Now, the reason why this is helpful is it allows us to see sort of how the reaction's actually proceeding. So what's happening here is the OH is attacking the carbon from an opposite trajectory that the bromine is leaving. And as a result, we get this product where the bromine leaves sort of along the same line or trajectory that the oxygen has been adding. What happens to the carbon is interesting. It needs to maintain its tetrahedral geometry. And as a result, it's going to sort of flip all of the hydrogens. So in this case, the hydrogens were all pointing one way. And then as a result of the reaction, the nucleophile comes in, they're going to have to spread out and flip over and face the other way. This maintains a tetrahedral geometry. Now, what we can do with this information is actually draw the structure of the molecule at the halfway point between bonds being broken between the carbon and the bromine and bonds being formed between the oxygen and the carbon. So what I'm going to do is consider that structure. So what's happening, what I'm saying is, let's consider a point where the oxygen to carbon bond is half formed and the carbon to bromine bond is half broken. Okay, and the hydrogen that's on the oxygen comes along for the ride. I'm not going to worry about it being a bent geometry for this particular example. Now, what's kind of interesting about this is that the atoms that are attached to the carbon are pointing either straight up or straight down. This is a trigonal bipyramidal geometry. Here. Get that spelling right. And this is the halfway point between the starting materials and the products. Note there are no intermediates for this reaction. And as a result, we just go from starting materials to products. Halfway between the two, we get to this point where we have half-formed bonds between the nucleophile and the electrophile and half-broken bonds between the electrophile and the leaving group. We would call this intermediate point. We would call this the transition state. Now, what's special about this transition state is it's actually a structure or geometry. But transition state, this is the same transition state that we learned about when we were talking about energy diagrams, right? The hills on the top of the energy diagram that separate the two valleys, those hills are the halfway point between the two valleys, and they're the point where we have our bonds half formed and half broken, halfway between our starting materials and the things that result from all the bonds being broken and formed. But what we have here is actually the geometry. Now what we do is we put a little double dagger above some brackets that are outside that structure, and that indicates that we have a transition state. So this is the symbol for the transition state. So it tells us that if we draw some structures and we put them in brackets with a double dagger over the brackets, we have the transition state for the transformation. What's important to note is we can't do this practically for all of the reactions. Many of the reactions have complicated transition state geometries, and so drawing them for each individual reaction would be cumbersome, to say the least. It gets to be quite daunting. But for the SN2 reaction, it's a simple transformation with no intermediates, and it goes through this transition state. What's nice about this transition state is we can use it to understand some of the other phenomena that are occurring. What I want you to do is I want you to think about the addition of the nucleophilic atom. So as the nucleophile is adding to the carbon atom and pushing the bromine off, this is kind of like wind on a very gusty, rainy day when you're trying to carry your umbrella. So you're carrying your umbrella and then wind is blowing back. And you know that feeling when you're like, I just want to get covered up from the rain, but then the wind blows the umbrella back and inverts the umbrella. That's exactly what this transition state is showing us. So and I'm going to delete that highlighting there. It's not super helpful long-term. So as the nucleophile adds, the arrangement of the electrophile carbon atom inverts. So it inverts. Now, where that's really important and interesting is in the context of stereochemistry. So let's talk about stereochemistry in the SN2 reaction. So stereochemistry in the SN2 reaction. So let's say we've got a chiral haloalkane, and we add to that a simple nucleophile, NaOCH3. Pretty simple, I guess. Okay, and we've got some solvent. Let's say we've got acetone, sure. Okay, what we want to do is, and maybe I'm put a sulfur here. I'm gonna make that DMSO. Sorry, that would have bugged me. Okay, so we're gonna mix these two things together, and first of all, we can go ahead and predict the product without considering the stereochemical ramifications. The negative charge is going to attack the carbon atom that is connected to the bromine, because that carbon atom is attached to an electronegative element, so it has a partially positive structure. When we mix the NaOCH3, the nucleophile, into solution, we're going to see dissociation of the ion pair, releasing the negatively charged oxygen atom to attack the carbon that it's attracted to, that carbon with a partial positive charge. However, during the attack, we're going to have to lose the bromine atom as a result of the reaction. And what we get is something that looks like this. The oxygen's added opposite of the bromine atom, pushing it off. And we could have Na plus floating around, sure. But ignoring the salt byproduct, if we look at the product that we formed, it's drawn a little awkwardly. Sometimes I like to practice drawing my products this way because it allows me to see, see where the connection points are. So then I can redraw this. And when you redraw it, you're probably just going to flip the chain that looked awkward so that we get this more natural zigzag structure, and the carbon that's shown with the dot has a structure more reminiscent of its true geometry, which is a tetrahedral center. But what we want to point out is that at this tetrahedral center, we have a stereocenter. This tetrahedral center is a stereocenter. And so what we should ask is it R or S? Okay. Now, it turns out that for most SN2 reactions, invert the absolute configuration. So most invert the absolute configuration. Now, this is a critical point. So what that means is when you hear absolute configuration, you want to think R/S. That is okay. But what I want that is okay, and it works about 90% of the time. But alternatively, what I would recommend is we flip the wedge/dash at the carbon with the halogen. So this approach will allow us to get the answer correct in nearly all cases. And by nearly, I mean I just am having a hard time thinking of a case. Assuming you follow, it just kind of makes your life easier. There are ways that I could trick you where the R and S rule wouldn't work. But 90% of the time, just flipping from R to S does work. But it also kind of implies that you have to figure out what R and S are, and you really don't. Okay, what I'm getting at is, I forgot a carbon up here, sorry. I'm just going to put OCH3 here. What I'm going to do is redraw the reaction up above so that we can see this. Now what I'm saying is OCH3 adds to the bromine and pushes it off. And then the outcome of the reaction is not this, because this has the same wedge and dash configuration. Rather, the outcome of the reaction is one where we have the nucleophilic atoms replacing the nucleophilic atom and then whatever is covalently bonded to it, replacing that halogen atom. And the product has the opposite wedge and dash configuration. It's inverted. That configuration has inverted from the starting material. So if you wanted to do R and S, just a quick analysis in my mind, this looks to be R in the starting material, whereas over here, this looks to be S. So we flip from wedge and dash. We don't need to determine R and S to figure this out. It might be a healthy exercise. It's always good to not forget things that we learned previously in this semester. But that's the inversion of configuration in kind of simple terms. Now, why does the configuration invert? I'll use words to answer this before we get to the pictures. The pictures will be a lot more helpful, but the words are important because these are words that chemists use all the time. So the answer to a question that I did not complete, sorry about that, invert, the nucleophile adds to the quote, and I didn't make this up because I wouldn't have, the backside of the electrophilic carbon atom. Adds to the backside of the electrophilic carbon atom. Another words that we use are backside attack. And again, I didn't make this up, of the nucleophile leads to inversion of configuration. Okay. So backside attack is responsible for the inversion of configuration that we see. What we're going to do on the next page of notes is just redraw the transition state that I had shown up above, but with a more complicated molecule. As you'll see, it doesn't make things that much more complicated. And again, just knowing that the stereochemistry, if there's a stereocenter at the halogen containing carbon atom, that will invert from wedge to dash or dash to wedge. Just knowing that will get you there most of the time. But let's explain why with some detail, especially if we can understand transition states, that gets to be very helpful. So using this reaction again, what I want to do is take the starting materials and consider the bromine. And now we're going to have three things, and let's actually make them tetrahedral-like. So they're just going to be going this way. Okay, so we are originally S. I think what we want to do is just have an ethyl group here and a hydrogen here. Okay, this looks to be still S if we started here. Now what we're going to do is we're going to have the, I'm going to just give myself some more space here. And shoot. So those are the same. Okay. So I have those same structures. Now what I'm going to do is take my negatively charged oxygen atom and let it come in and attack along the same trajectory that the bromine is going to be leaving. Now when I do that, you're going to get a transition state geometry where the methyl group is drawn straight down, the ethyl group is drawn straight up, and the hydrogen is right behind that ethyl group. We're going to have the bromine being pushed off, and we're halfway from the bromine being pushed off and the oxygen atom being fully connected, and they're adding across the same trajectory. This is the wind on a rainy day that is taking our umbrella that's shielding us and popping it open. Okay, so you have your umbrella, the breeze hits it, it spreads. There's a moment, there's a transition state as the umbrella inverts to where it flips over and it looks like this. So that's what we want to think about. The nucleophile is the wind on the rainy day, flipping our umbrella. So what is this structure that I have drawn? This is the bracket with the double dagger. That is our transition state. Transition state. Okay. So after the H3CO has added fully to the carbon atom, the ethyl group is going to be pointing this way along with the hydrogen, and the methyl group is over here. And what we'll do is we will redraw this product so that it looks like a normal bond line structure. And if we look now, this is R, the way that we would prioritize that. Or in other words, we could have taken the original orientation of the molecule and connected the OCH3 in the same spot that the bromine was at, just substituting them, the OCH3 and the bromine, just replacing the bromine with the OCH3, let me phrase that correctly, and having the connectivity and orientation the same, except we're flipping the wedge to the dash at the stereocenter. So the inverted umbrella, if you think about it, this up here, this is the backside attack. And now this is our inversion of configuration. Happens in the transition state. And now we have inverted stereochemistry in the product. Okay. So what I think I want to do is let's stop the video there. That's long enough. And then in the next video, let's practice several examples where I just kind of show you some starting materials, some products. Some are going to be chiral, some are going to be achiral. Let's go ahead and just do a few SN2 reactions so that we get comfortable predicting the products and proposing the mechanism.